Swayam Prabha. Digital India. Educated India.
Let us construct a 2D crystal by showing this video example. So here we have a 2D crystal which is infinite along the two directions, which has been generated by two basis vectors A and B, and the motif is a two circle motif. So let us see how this crystal is constructed. So first we impose the lattice translation vector along the x direction. This is done infinitely along the x direction. Then we impose the lattice translation vector along this row of these two spheres along the y direction. It is to be noted that the position of the motif relative to the lattice point is exactly identical as we go from one lattice point to the other. Let us revise some of the aspects we have considered so far, especially with regard to crystals. We have seen solids based on atomic structure can be amorphous, quasi-crystalline or crystalline, and in this current topic we will extensively deal with crystalline structures. We had considered the motivation for studying crystalline structures, as we see that many of the important engineering materials like metals, semiconductors and ceramics are crystalline in nature in their usual form. We had also seen that some of these can also be obtained in non-crystalline forms. We had also talked about the language of crystallography, the language which is used to describe crystalline structures, and we had seen that it is a language of succinctness, it is a language of terseness, wherein we try to represent an infinite crystal in a very finite form in as little as information as possible. So let us try to track the keywords which we had dealt with, and the first definition we had given, the important definition, was that a crystal is a lattice plus a motif. So there are two keywords here, and let me write them down on the board for your continuous reference. We had mentioned that there is a synonym for a motif which is called a basis, and we had further mentioned that we will try to avoid this terminology, but as it can lead to a confusion with the term basis vectors, and so we will use the terminology motif whenever we are trying to represent something which is going on to decorate a lattice, which will finally give us a crystal. The second definition, which we had briefly mentioned, and perhaps we will not go into a lot of detail in this course, is the definition of crystal, wherein we invoke the concept of a space group and an asymmetric unit. So a crystal, according to the second definition, is a space group plus an asymmetric unit. The second definition, which is based on symmetry, becomes important especially when you are trying to classify crystals, and one of these classifications we will consider that there will be 7 types of crystal systems. And once we have defined a crystal in a rigorous form, the way we have said here, we should typically avoid loose and improper definitions of a crystal, as this can lead to a lot of confusion. An important point we had said was that initially we would start with dealing with ideal mathematical crystals, and later on in various ways we will relax the conditions which are imposed by this ideal mathematical crystal and try to develop what we might call real or practical crystals. It is very clear that any crystal found in nature is obviously not a mathematical crystal. A mathematical crystal is a construct of our mind, and as we see, one of the conditions which straight away cannot be met when we are talking about a crystal is the infiniteness. No crystal can be infinite. But we will see there are other conditions we will relax as well and go from an ideal mathematical crystal, which we are going to learn first, and then we will construct these more practical crystals, and that will be our goal of future lectures. So let us look at the definition of a crystal as a lattice plus motif. That's what we had done. We had said that lattice tells us how to repeat and the motif tells us what to repeat. This is what we had considered, and we had gone into quite a considerable depth to understanding what kind of motifs are possible which can go on to decorate a lattice. We had made an additional point that the motif is merely associated with a crystal, a lattice point, and need not actually be positioned on the lattice point. So this is a subtle point, but nevertheless important in understanding crystals. So among the two keywords we have listed on the board, the lattice and the motif. So we need to understand the word lattice first. Typically lattices are also called space lattices, and an array of points in space such that every point has an identical surrounding we define as a lattice. And we also said that in Euclidean space, that is flat space, and such an array would be infinite. Often we may also see definitions of a lattice as a translationally periodic arrangement of points in space, which we call a lattice. We had also constructed a 1D lattice, which is perhaps the simplest lattice, and we saw that it is infinite in 1 dimensions. We had seen that how actually we can construct a 1D lattice starting with 2 points, wherein we impose the condition that every point has to have identical surroundings. So the criteria that every point has to have identical surroundings automatically leads us to an infinite lattice in 1 dimension. And we also saw that such a lattice, a 1-dimensional lattice, is described by a single lattice parameter, a single lattice translation vector, which can be A, the vector, or if you are talking about the lattice parameter, the modulus of A, which is this A without the vector sign. So a lattice in 1 dimension needs just one parameter to describe it completely. Then the second keyword in the definition of a crystal is the motif, and we wanted to understand what can constitute a motif. So an important point we had made, though we did not take it up in detailed consideration so far, was that any entity associated with a lattice point is called a motif. Such a entity could be a geometrical object, and we consider some examples as we will see in the next slide, or a physical property, or it could be a combination of a geometrical object and a physical property. The geometrical objects could be a pentagon or any irregular object as well. But we also made a point that typically in atomic crystals, which is, as we see in future lectures, is of considerable importance to this course, could be an atom, it could be a group of atoms, it could be ions, it could be molecules. These molecules could be small molecules or could be a large molecule, or in some cases, as we may consider some examples, it could be an entire virus, which could be a living organism. So a living organism like a virus could be crystallized, and therefore it could be as large an object as a virus. An important point about dispositioning of the motif with respect to the lattice points we considered was that it has to be positioned identically with respect to each lattice point. We are not allowed to rotate, distort, or any way tamper with the motif we are placing at each lattice point. Of course, if the object has certain kind of symmetry, those symmetrical rotations would be irrelevant. So to summarize the important point of a motif, it could be a geometrical entity or a physical property, and a typical physical property could be a magnetization vector, and you could have cases wherein the motif is actually a combination of a geometrical entity and a physical property. So some of the examples of motifs we considered were, on the left hand side are some geometrical motifs, and we saw the only possibility in 1 dimension was a length segment. In 2 dimensions you could have various shapes, regular or irregular. Some examples of regular shapes could be a pentagon, a square, a hexagon, or a heptagon. In 3 dimensions you could have various shapes, and this could be a cube or a cylinder or a sphere or any one of these. It was also important for us to consider atomic motifs as listed on the right hand side, and we saw that they could be a single atom like an argon atom, there could be a single ion, there could be a group of ions or a group of atoms, and there are a group of ions. An example which of course we will consider in detail later is the example of a sodium and a chlorine ion. The sodium ion being positively charged and the chlorine ion being negatively charged. So we see that there is considerable variety when it comes to the various kinds of motifs which are possible. We also constructed some one-dimensional crystals, and an example is shown here, wherein we start with a line segment which we use to decorate a one-dimensional lattice, and the crystal obtained is a one-dimensional crystal. So the only variation we have in terms of the motif here is the length of the motif here, which is one-dimensional, and the only variation possible in terms of the lattice is the lattice parameter. So these two possibilities with regard to the lattice and the motif can give you a variety of crystals all in one dimension. To emphasize the fact that a motif actually need not be physically positioned on the lattice, we considered the fact that we could actually move the motif with respect to the lattice by a certain shift, which is seen here, and position it with respect to the lattice. The crystal in any sense has not changed from the previous crystal. Its description would be exactly identical as the previous crystal, but the only difference is the way we have put the motif relative to the lattice point, and this is just a convenience we may use for certain reasons, but nevertheless the crystal we have obtained is exactly identical to the crystal we had previously obtained, wherein we had placed the motif directly on top of the lattice point. We said that we could actually relax the condition of a strict one-dimensional motif. That means we could have two-dimensional motifs and three-dimensional motifs which we can use to decorate a one-dimensional lattice, and we are doing so to have a better understanding of crystals here at this point of time. And an example here was a circle which we had used, which could be a two-dimensional motif, or it could be a sphere which is a three-dimensional motif, which can go on to decorate our lattice with lattice parameter A. So the crystal obtained is shown in the bottom, and truly speaking it is a two-dimensional or a three-dimensional crystal, as the motif is of a higher dimension than the one-dimensional lattice we started off with. Then we went on to understand a slightly more complicated motif, and we will consider this motif again and again in various contexts to understand various kinds of important concepts which come in crystallography. And this was the example wherein we had an up arrow and a down arrow decorating a lattice with a lattice parameter A. We had said that the motif in this case is an up arrow and down arrow with a spacing between the components of the motif being a by 2. An important point which came here was the point we had mentioned slightly before, that some parts of the motif or the entire motif actually need not sit on the lattice point. In this case, the down arrows do not sit on the lattice points. It is only the up arrows which sit on the lattice point, which brings us to the important consideration that not all centers of these entities are lattice points. Only the up arrows centers are lattice points. Of course, we could also do an alternate trick, that we could choose the centers of the down arrows as lattice points, but having chosen either the up arrow center or the down arrow center, we can use only one of the two as the point for a lattice. Of course, we can choose the lattice point somewhere in between the two also, but for simplicity we will assume that here that the center of the up arrow is a lattice point, which automatically implies the center of the down arrow is not a lattice point. So we shall revisit this kind of a crystal to understand more concepts later. So we had also gone ahead and sort of cleared our fundamentals on this very problem of an up arrow and a down arrow by stating that not all points which were originally we started off with, if suppose we had started off with an array of points which are spaced a by 2, then after the crystal has been constructed, then not all centers are lattice points, and that is what we had exemplified using the figure at the bottom. Then we went on to create 2D crystals, and we had done so to understand more concepts which could not be clarified in the case of an 1D crystal. So we said a strict 2D crystal would be a combination of a 2D lattice and a 2D motif. Of course, like as we had done for the 1D crystal, we can relax the conditions and try to put 3-dimensional motifs on a 2-dimensional lattice to create a crystal. So the first example we considered of a 2-dimensional lattice is as shown on the left. We had seen that there are 2 vectors we need which are not collinear to generate the lattice. Okay. These vectors are A and B, the A vector along the x direction and the B vector along the y direction. And this lattice, though it has not been shown here, it is infinite in 2 dimensions, and only a part of the lattice is shown here for us because we cannot draw the entire lattice on a screen. So there are 2 basis vectors, and in the current example the angle between the 2 basis vectors is 90 degrees, but as we shall see soon, this angle can be any arbitrary angle for a general lattice. The motif we had considered was a 2-dimensional motif which is in the shape of a green pentagon. As we had seen, any other 2-dimensional shape, regular or irregular, could have sufficed in understanding or in the process of making a 2-dimensional crystal. So starting with this 2-dimensional lattice which has been generated with 2 basis vectors which are not collinear and the motif is in the shape of a pentagon, we went ahead and created a 2-dimensional crystal. And like in the case of a 1-dimensional lattice and the 1-dimensional motif, there are many ways of associating this motif or overlaying this motif on the lattice point, and one of them has been chosen here, wherein the tip of the pentagon is the point which coincides with the lattice point. One point which is very, very clear while we did this, just to reiterate, that we are not allowed to rotate or distort the pentagon as we go from one lattice point to the other. And once the crystal has been created, as the lattice is infinite in 2 dimensions, the crystal is also automatically infinite in 2 dimensions. Now, an important point which comes out when we look at this crystal is that it has got 2 kinds of important order. One is that it has got positional order, which is clear from the fact that each of the motifs is sitting identically on the lattice point, and it has additionally got an orientational order. The reason for us to consider this positional order and the orientational order is that when we go from these mathematical crystals to real crystals, we may call something a crystal even when some of these criteria are relaxed. That is, we want to go from ideal mathematical crystals to real crystals, then some of these criteria would be relaxed. That means we may consider either one of the 2. We may only consider the orientational order, or we may only consider the positional order in the definition of a crystal. So the important property here was the orientational order and the positional order of a crystal. We had seen that these crystals are infinite. Therefore, we need a method to succinctly represent the crystal, and the method we had suggested was to choose a unit cell. We have a unit cell and we have the basis vectors. So unit cell is nothing but a part of the infinite lattice or a part of the infinite crystal. So unit cells can represent a lattice or they can represent a crystal, and when added, superimposed on them the repeated translation vectors, 1 in 1 dimensions, 2 in 2 dimensions, we would get a crystal or a lattice depending on the unit cell you start off with. We had said that the word unit should never be confused with the fact that there is one lattice per or one motif per cell. Whenever you have only one lattice per cell, such a unit cell is called a primitive unit cell, and the word unit merely represents the fact that it is an unit of the entire structure. So it is like a building a brick of the wall. Starting with the brick, you can construct the wall. Similarly, starting with a unit cell, you can construct the entire lattice or the entire crystal, and therefore it is called a unit cell, and not because it has only one lattice point per cell. Another important point which we considered was that in a typical unit cell, we may have the entities broken into pieces, and we will see that in the examples, or we had seen that in the examples which we had considered before. Some of the points we had considered when considering unit cells is the fact that in a typical unit cell you have only lattice points at the corners. If you have one-dimensional unit cell, at the ends of the unit cell segments you would have lattice points, and this is a convention. And later we had also considered some examples of unit cells wherein the lattice points did not sit at the vertices. If the lattice points only are at the corners of the unit cell, we called it a primitive unit cell, and otherwise if there are more than one lattice point per cell, we called it a non-primitive unit cell. We also pointed out there are other kind of unit cells or cells which people consider, which are Voronoi cells and Wegener-Sage cells, and we will not typically deal with these in this elementary course. So we further went on to take up the example of a one-dimensional lattice, and we tried to understand the primitive unit cell, the doubly non-primitive unit cell, and the triply non-primitive unit cell. As you can see, in the primitive unit cell, we pointed out that the lattice point per cell is 1, half coming from the left hand lattice point, half coming from the right hand lattice point, totaling up to 1 lattice point per cell. In the doubly non-primitive unit cell, the entire contribution of central lattice point to the cell exists. The one on the left and one on the right contribute half each, contributing a total of 2 to the unit cell. A triply non-primitive unit cell similarly would have a contribution of 3 lattice points per cell. We had also said, since there are only kind of motif possible in 1D is a 1D line segment, if real crystals are made even on 1 dimensions, they would actually be having a 3-dimensional motif typically on the 1-dimensional lattice. So let us consider, at this point of course it may be worthwhile just as a aside to mention that it has been proved that 1-dimensional crystals are not theoretically possible. So let us consider the example of a 1-dimensional crystal as shown here, and we wanted to see that actually in the unit cell we have only half the circle or the sphere coming inside the blue line, which is the unit cell, and the right hand side again there was a half. Put together these two halves, you have 1 circle per unit cell and also correspondingly 1 lattice per unit cell. A point again noteworthy at this stage is that typically sometimes we draw unit cells the way it has been shown here, wherein you draw the complete circles, keeping of course our understanding at the back of our mind is that that is just a simplified representation and the real unit cell should look like the one which is shown here. We also considered two-dimensional unit cells, and we said we require 3 lattice parameters to describe a 2-dimensional unit cell, the 2 length scales A and B, and include an angle between them alpha. We also said that there are typical cases or special cases wherein you have special constraints on the distance lattice parameter or special constraints on the angles. The special constraints on the angles could be 90 degrees or 120 degrees, while in special cases A could be equal to B. There are 4 types of unit cells which are observed in 2 dimensions. These are the square, the rectangle, the 120 degree rhombus, and the parallelogram. In the square unit cell, A equal to B and alpha equal to 90 degrees. In the rectangle unit cell, A and B are arbitrary numbers which are not equal to each other, and alpha still is equal to 90 degrees. In the 120 degree rhombus, A is equal to B, but the alpha has a special constraint on it that it should be equal to 120 degrees. The parallelogram unit cell is the most general unit cell possible, wherein A, B and alpha are 3 parameters which have no constraints placed on them. So as we are listing keywords on the board, let us go down to the board and write down the special keyword, the word unit cell. Let us consider a 2-dimensional lattice as printed on this sheet of paper. We will try to generate a 2-dimensional crystal as we have done on the computer before. For this sake, I have got a pile of 3 discs, and for now you should have to assume that these 3 discs are of the same color. Therefore, we will assume that there is no difference in color, and therefore they can constitute an ideal motif which is something like a 2-dimensional motif, and I will decorate this 2-dimensional motif on this lattice as you can see to generate a 2-dimensional crystal. As this motif has got circular symmetry, it does not matter if I rotate the motif with respect to the one motif with respect to another motif. But suppose this were of a different shape, like the shape shown here, then I am not allowed to rotate this motif from one lattice point to the other. In that case, I will have to identically place the motif, and I cannot rotate the motif as I go from one lattice point to another. But for now, I will continue making this crystal with these set of discs which I have got with me here. So, as we had seen the problem before, that such a crystal would be infinite, and all I can do best here is to only take a finite representation of this crystal to generate this two-dimensional crystal. As you can already see, the generating an ideal mathematical crystal on a sheet of paper can be tricky, and there could be in practice certain distortions which would allow the practical crystal to be slightly different from the ideal mathematical crystal which we have been describing on the computer. As we are running out of discs, I will stop here and not try to fill the whole of this two-dimensional sheet of paper. It is clear that the unit cell for such a two-dimensional lattice would be this one square which is here, which is the square which I have tried to shade here. After considering this two-dimensional crystal, let me try to focus a little bit of attention on the unit cells which we have chosen for the two-dimensional lattices and the two-dimensional crystals. So, I got some models here with me. These models, as you can see, consists of balls and magnets, and this clearly is an example of a square unit cell or a unit cell of a square lattice. So, if such a unit cell is repeated, we would actually get a two-dimensional crystal. If you want to go from this square unit cell and actually consider a rectangle unit cell, this is exemplified by the rectangle shown here. Of course, this is a very special rectangle wherein the length is a certain fraction of the width, but in general rectangle unit cells could be of any arbitrary shape, the only constraint being that A should not be equal to B. In both cases, you can clearly see the included angle between A and B is 90 degrees. I can further perform a simple experiment of trying to distort this unit cell. So, once I distort this unit cell, clearly now this unit cell has transformed into a parallelogram unit cell. This included angle can be any angle depending on the kind of distortion I am imposing on this, and even after the distortion you can clearly see that the two opposite sides are parallel, and therefore this is a parallelogram unit cell of the most general type, wherein there is no constraint either A or B or on the included angle. Now, suppose I take this square unit cell, but now perform a very special kind of distortion wherein I will try to match this distortion and try to create a rhombus out of that square. When I try to create a rhombus, obviously since the distortion is not going to change the length of the four sides, it will remain as such, but the distortion I will carry forward till the included angle between the two sides becomes 120 degrees, and that is what I have done here on the right hand side. You clearly see this is a unit cell of an 120 degree rhombus, and after making a distortion I have put in the plastic piece which is shown here to actually show that this is now constrained to 120 degree, and therefore you can have a 120 degree rhombus unit cell starting with a square unit cell merely by a distortion of it such that the included angle becomes 120 degree. After considering some simple practical models, we will return to our discussion of 2D unit cells. We have seen that there are primitive unit cells, doubly non-primitive unit cells, and higher order non-primitive unit cells when we talk about lattices. In the case shown in the figure, we have a two-dimensional rectangular lattice wherein the blue unit cells are primitive unit cells and the brown shaded ones are doubly non-primitive and the orange shaded ones are triply non-primitive unit cells. An important point which we make here, and perhaps we will return to it again and again, was the fact that our choice of the unit cell either for a lattice or for a crystal is not going to alter anything about the structure we are considering. just because I use a unit cell for the on the blue color shown on the right hand side, which is of the shape of a parallelogram, our unit cell or our structure is not going to change in any way, and it will be equally well to represent it in any other form of the unit cell, irrespective of its primitive or non-primitive. So all possible shapes of unit cells are possible, but there are other unit cells which are we call preferred unit cell, which we will use often. So let me emphasize this perhaps obvious but important point: symmetry of or the kind of a lattice or the crystal is not altered by our choice of the unit cell. So this is a simple but very important point. Now how do we go about choosing unit cells? As we have pointed out, there are infinite ways of choosing unit cell, even for a very simple structure like a two-dimensional lattice. But there are certain guidelines which helps us in choosing a unit cell, so that when we make what we may call a convention, so that when we communicate with each other, we have a standard unit cell which we can refer to. So the first criteria which typically used is the criteria of symmetry. We try to choose a unit cell which has the maximum symmetry, and typically the symmetry of the unit cell would be same as the symmetry of the lattice or the crystal we are considering. The second criteria we imposed was that the size of the unit cell, we will try to keep it to a minimum, and if both of these criteria fail, then we try to settle down on a convention wherein we resolve the issue by choosing a unit cell which we call the standard unit cell for a particular kind of structure. So the three factors are symmetry, size, and convention. So suppose I have a lattice here as shown here. We have something like which looks like a centered square lattice. We can choose a doubly non-primitive unit cell or a blue unit cell which is a primitive unit cell. In this case, the symmetry of both the unit cells is exactly identical. As you can see, both of them got a four-fold axis in the center. The mirror planes and other symmetries are also identical for the two unit cells. And now when we are talking about the symmetry of unit cell, it should not be confused with the symmetry of the lattice or the symmetry of the crystal we are describing using the lattice. It is merely the symmetry of the unit cell we are talking here. Since the symmetry of these two unit cells is identical, we would go ahead and choose the one which is on the right hand side, the blue unit cell, which is the smaller unit cell. Yes, you would have noticed all I have done in this case actually drawn a square lattice at an angle of 45 degrees, which makes it look like a centered square lattice. In the same case of the square lattice, we could have chosen certain other kind of non-primitive unit cells as shown in the figure below, in which case this is a parallelogram unit cell. Clearly this is not a preferred choice, as this parallelogram unit cell only has a two-fold axis at its center, while the other two unit cells have four-fold axis at the center. Therefore we would definitely not go ahead and make a choice of the parallelogram unit cell, even though it has a size which is identical, size in this case implying area, which is identical to the primitive unit cell. For the sake of understanding, I have also drawn some of the four-fold axis of the lattice on the same figure. Now suppose I have a centered rectangular lattice which are generated by two basis vectors a and b. Therefore this lattice has only two-fold axes and there are no four-fold axes in this, and the lattice parameters are a and b, which are not equal, and the included angle is 90 degrees. The unit cell which we choose for this case is a centered rectangular unit cell, and even though we have a smaller unit cell at our disposal, which is the primitive unit cell, which is of the shape of a rhombus, we typically choose the rectangular unit cell. We will have a little more to say about this later, because in this case, as it happens, both the unit cells have the same symmetry, the primitive rhombus unit cell and the rectangular unit cell, but we don't go for the smaller unit cell. We actually use the convention that we will actually use the bigger unit cell which has a shape of a rectangle. So this, in this case, actually the convention which comes to the fore, because the rhombus shaped unit cell and the rectangle shaped unit cell both have a two-fold symmetry, for instance at the center of the unit cell. Now let us consider how to choose a unit cell for a crystal. So we have a simple rectangular lattice as shown in the figure on the left, and we want to generate a crystal by putting a motif which consists of a green circle and a brown circle. So, by putting this, we have now obtained an infinite two-dimensional crystal. The unit cell can be chosen in many ways as before, but one choice is clearly not true, which is the one which is shown on the right hand side here. You cannot choose as a unit cell, as the corners of this rhombus are not lattice points. If we choose the center of the green circle as a lattice point, then the center of the brown circle cannot be a lattice point, and therefore we had stated that in conventional typical unit cells, all the vertices have to be lattice points. This cannot be a unit cell. This unit cell is not a centered unit cell, but a primitive unit cell again, because the center point is not a lattice point, and this such a unit cell has only one lattice point for this blue cell. And we had also noticed that in this unit cell you can define the shortest lattice translation vector as the one which is shown here by the brown line. We will return to the concept of a shortest lattice translation vector when we deal with dislocations especially. We have shown in this example that the B vector is actually longer in length as compared to the A vector. And this is the way we typically show this unit cell, and we had clearly mentioned that the preferred or the more correct way to show this unit cell would be the way it is shown in the bottom diagram, wherein the circles have been cut into 4 parts and placed at the 4 corners of the unit cell. The contribution of the green and brown circles to the unit cell has not changed. All merely has changed is the representation. So, this is also tells us an important example that the unit cell may have entities going on to decorate the lattice in parts, and therefore we should be little careful in understanding the unit cells if it is drawn in the way it is shown here. It does not mean that the atom has actually, if suppose the decorating entity was an atom, it does not mean that we are actually cutting up an atom and placing it in 4 parts. It is merely a representation of the unit cell. We had asked another question in the previous lecture, that should a unit cell have lattice points only at the corners? We said that in a typical conventional case we only keep lattice points at the corners, but for special reasons we may want to choose unit cells wherein lattice points are not just present at the corners, but there are alternatives possible as shown here. So, the 3 alternatives which are shown here, one is the yellow colored unit cell, one is the blue colored unit cell, one is the green colored unit cell. All 3 are possible space filling geometrical entities. In this case they are 2-dimensional entities, and the only requirement that a cell can perform the role of a unit cell is that it has to be space filling. That means the structure, after putting this unit cell with along the x and y direction lattice translation vectors, we should not be left with any gaps in the structure. So, we can clearly see, for instance, in the example shown, that the green unit cell is a space filling unit cell, but it is also clear that the 4 corners of the green unit cell do not contain lattice points. A nice way of understanding this is that the one nice thing which comes out of taking unit cells like this, it is clear from this that these unit cells are primitive, because clearly there is just one included lattice point inside the unit cell. There is one included lattice point inside the yellow unit cell, there is one included lattice point inside the green unit cell. In the case of the blue unit cell, there are 2 halves contributing to the one lattice point per cell. And we had said that suppose you are not interested in cutting up the entities in representation of the unit cell, then such a choice of unit cell, the one on the left hand side has shown entities in cut form, the one on the right hand side shows that the unit cell has one green circle and one brown circle, which is what we understand from the fact that it is a primitive unit cell. Let us now consider a space lattices in little more detail before we actually go down and start understanding 3-dimensional structures, which are the typical crystal structures which are of importance to us. This definition of a space lattice we have already considered, and I will merely restate that a space lattice is an array of points such that every point has an identical surrounding. We had also considered some one-dimensional lattices as shown in the figure, and we had stated that the unit cell has a lattice parameter which is given by A. We had also considered some 2-dimensional lattices, and we had said that there are 5 distinct two-dimensional lattices. So this is the new point we are considering here, that the two-dimensional lattices which can be constructed with two basis vectors and which are infinite in 2 dimensions, there are 5 different two-dimensional lattices which are distinct from one another. These 5 two-dimensional lattices are the square lattice, the rectangle lattice, the centered rectangle lattice, the 120-degree rhombus lattice, and the general parallelogram lattice. An important point which is to be noted here is that we had previously used some of these terms like the square or the rectangle in the context of unit cells. At no point of time there should be any confusion between the shape of a unit cell and the kind of lattice we are considering. Often this has been the core reason that some of the important understanding is obscured by the use of same term for two different kind of objects, one in this case being a unit cell whose shape is being described, the other being a lattice. And we had clearly stated that the lattice will remain unaffected by our mere choice of a unit cell of one type or the other. So to reiterate, there are 5 types of lattices in 2 dimensions. These are the square, the rectangle, the centered rectangle, the 120-degree rhombus, and the general parallelogram lattice. In some of these slides we will see that we will not consider all the symmetries overlaid on the lattice, but typically, for instance, we will omit glide reflection and other kind of complicated operators which involve translation, but typically we will only superimpose mirrors and rotational symmetries, which will be suffice for us to clarify the points we need to make. So before I leave this slide, let me reiterate this point again, that this common terminology between lattices and the shape of unit cells can be a cause for considerable confusion, and it should be at every point of time clear that even though this word use square is also used for an unit cell, there should be no confusion that the square lattice is a different kind of entity as compared to a square unit cell. So we had already said that 2-dimensional lattices are generated by 2 basis vectors with an included angle, and in the example shown in this slide, this included angle alpha happens to be 90 degrees. We had also seen that 4 unit cell shapes are typically used to describe these 2-dimensional lattices. We will have a few more things to say now before we go ahead and actually take up the 5 different 2-dimensional lattices in detail. That we have these 5 2-dimensional unit cells, it is clear that some of them we have expenditure of more lattice parameters as compared to some of the others, and some of them have a certain constraint on the angle. So we want to put some of these unit cells in certain order, and the parameter we choose to define this order is a parameter we call terseness, so that we can order these unit cells, and clearly this order will help us understand that some of them are somehow more symmetric than the others, or some of them have a lesser expenditure on parameters. So we will define some parameters to understand this terseness. We will define something known as a P prime, which tells you the number of independent parameters required, which is nothing but the number of parameters and number of equations which connect some of these parameters. In other words, if there are equal to signs anywhere in the parameter, then that will go into the contribution of E. C will be the number of constraints, and if there is some positive constraint, then the number C will increase. We will define terseness as the difference between P and C, which is the number of parameters minus the number of constraints. So terseness tells us that what is the measure of the expenditure on the parameters. More the expenditure on the parameters, then lower will be its place in terms of the lattice parameter tree. Let us consider the square lattice, wherein the number of, in all these cases, the number of independent parameters is 3, which is the A, B and alpha, and we have 2 equations which connect them, as you can see. So the number of constraints is 2, so 3 minus 2 is 1, which is the terseness value for the square lattice. If you consider the rhombus lattice, the number of independent variables is 3, the number of constraints, one of them being for the A equal to B, the other constraint being on the angle, which is 120 degrees, Therefore, the difference between 3 minus 2 is 1, and therefore the terseness value for the rhombus lattice is also 1, which is why the square lattice and the rhombus lattice have been placed on the same level. Now, if you look at the rectangle lattice, there are 3 variables, and the number of constraints posed on these variables is that A is not equal to B, that means it still remains general, while the alpha angle has been constrained to be 90 degrees. Therefore, 3 minus 1 is 2, the terseness value is 2, that means we are having more expenditure in this case of a rectangle as compared to the square on the parameters, and therefore it comes down as compared to the square or the rhombus in terms of the lattice parameter expenditure. If you look at the parallelogram lattice, the A, B and alpha are all general, that means the number of constraints is 0, therefore 3 minus 0 is equal to 2, the terseness value is 3, and therefore the parallelogram lattice falls at the lowest level as far as the expenditure on the lattice parameter goes. So, this slide basically tries to tell you that we have a certain expenditure on lattice parameters, and therefore more the expenditure, lower will that unit cell be in the tree, and based on expenditure the square and the rhombus are at the top of this tree. So, let us now consider the 5 two-dimensional lattices one by one. So, shown in this example is a square lattice. In the case of a square lattice, there are 2 vectors which go on to generate the lattice, but the important thing is that the modulus of the A vector is the same as the modulus of the B vector. In other words, A is equal to B. The included angle alpha is 90 degrees, and this is the characteristic of the two-dimensional square lattice. If you look at the unit cell of the square lattice as shown in the blue color here, we can overlay some symmetry operators, and what we have done is that we have not overlaid all the possible symmetry operators on the square lattice. This is so that there is some clarity in thought, but given the fact that if there is a symmetry operator sitting here and there is a lattice translation vector A, that means there has to be another equivalent symmetry operator which is a 4-fold which has to sit here. Similarly, if you have a green colored 2-fold axis sitting here, and if you have the A lattice translation vector, in this case I would consider a minus A, then automatically there has to be a green 2-fold axis which has to sit here, and correspondingly here, correspondingly here, correspondingly here. In other words, if I can locate one symmetry operator anywhere in the lattice, then this symmetry operator would also go ahead and completely fill up this 2-dimensional lattice or space given these 2 lattice translation vectors. So, there will be a 4-fold here, there will be another 4-fold here, there will be another 4-fold here, and so forth. This 4-fold is not actually sitting on a lattice point, but is at the center of the unit cell. So, if I now impose the A translation vector, the minus A in this case, I will have one more 4-fold at this position, and if I translate it by B, I have one more here. This is nothing but stating the fact that whatever is contained within a unit cell has to be repeated. In the previous cases, what we considered was motif which was contained in the unit cell and which was repeated by the lattice translation vectors. In this case, it is not the motif, but the symmetry operators of the lattice. Clearly again, to re-emphasize, we are now considering the symmetry operators of the lattice and not the symmetry operators of the unit cell, okay, or the symmetry of the unit cell, and therefore the unit cell will just repeat all the symmetry operators which are contained within it across the entire 2-dimensional lattice. For sake of clarity, I have shown here the 2-dimensional unit cell here along with the overlaid symmetry operators, the rotational symmetry operators. So, you can see that all 4 corners and the center contain a 4-fold rotation axis. The centers of the edges contain a 2-fold rotation axis. Further, if I want to overlay the mirror planes on top of this unit cell, then we can consider unit cell which has been shown below. As before, the 4-fold axes continue to be at their original positions. So, the 2-fold axes which continue to be at their original positions as in the unit cell before, but additionally we got these mirror planes which are shown by these red lines. So, the edges of the cell are also mirror planes apart from the ones which are shown by these red lines which go past to the center of the unit cell. There are 2 distinct mirror planes, the one which is vertical and the one which is inclined at an angle of 45 degrees. We do not have to consider the horizontal or the other diagonal, because if I consider the vertical mirror plane, then the fourfold axis will take the vertical mirror plane to the horizontal mirror plane. Similarly, the one diagonal mirror plane will be taken by the fourfold to the other diagonal mirror plane. The shorthand notation of describing this kind of a symmetry combination is shown in the blue rectangle, which is nothing but 4 mm. The 4 standing for the fourfold axis, 2 mm standing for the M1, which is a vertical mirror, and the M2, which is a diagonal mirror. A question which obviously comes to mind is that why do we put rotational symmetry elements onto a lattice? Aren't lattices supposed to be constructed only of translational elements? This is an important question. It is true that lattices are built out of translations, as in this case it's a and B lattice translation vectors, but once the lattice has been generated, we will notice that the lattice will have certain symmetries, and this is very, very important for us to observe these symmetries and note them, because our classification of crystals is typically based on these symmetry operators. So to emphasize the point, I will ask myself this question again: why do we put in rotational symmetry elements onto a lattice? And in addition, of course, I could put in mirror and other symmetry operators on lattice. The question we are asking is that why do we put these kind of symmetry operators onto a lattice, while the only kind of symmetry which was required to generate the lattice was the translation? The answer to this question is that it is very important that we actually overlay these symmetry operators on the lattice, because when we try to classify the crystals made out of these symmetry operators, symmetry is of paramount importance, more so than even the translation which originally created it. So in all future considerations of lattices, we will typically try to overlay the symmetry elements on the lattice, and we will try to understand later how these symmetry elements come in very handy in classifying lattices and crystals based on that. Worthwhile point maybe at this stage, which we will revisit of course in detail later, which is again related to the fact of the symmetry of the lattice and the symmetry of the crystal. The symmetry of the lattice is what we considered before, is nothing but the 4 mm symmetry. Now the lattice will always, a square lattice that is, will always have this 4 mm symmetry, irrespective of what motif I use to decorate on the lattice. So the underlying lattice has this 4 mm symmetry, but however the crystal based on this lattice can have a symmetry lower than that of the lattice. This is a very, very important point, so I will repeat the sentence. Crystals based, for instance, in this example on the square lattice can have a symmetry which is lower than the symmetry of the lattice. For instance, I could place a motif on the lattice such that the crystal has either a 4 mm symmetry or a symmetry which is just a fourfold. Then the crystal which I generate, I will call it a square crystal, otherwise I will not call it a square crystal. We will of course return to this point in detail later. So at this point, all I need you to understand that there are more considerations than just the symmetry of the lattice or the shape of the unit cell of the lattice which go into defining crystals, and if I place a motif of a lower symmetry than the symmetry of the lattice, then that motif can alter the symmetry of the crystal I have generated, and the original symmetry of the lattice may be lowered or may even be completely destroyed. So to re-emphasize, based on the symmetry of the motif which I put on the lattice point, the symmetry of the crystal which I generate from the lattice may be lower with respect to the, may first of all of course remain same as the symmetry of the lattice. It may be lowered, or in an extreme example may be completely destroyed. And when I am talking about completely destroyed, I am talking about these mirror planes and rotational symmetries and not the translational symmetry. Of course, if I have no translational symmetry in the final crystal which I have created, such a structure is called an amorphous structure and not a crystal. The second in the list of lattices is the rectangular lattice. The rectangular lattice is generated by two basis vectors A and B, which are at an angle of 90 degrees. The rectangular lattice has no fourfold axis, it has only twofold axis, and with respect to the lattice points, as you can see, there is a twofold axis at the lattice point, there is a two-fold lattice between two lattice points, and there is a four-fold axis which is between four lattice points which form the corners of the blue unit cell as shown. In the case of this rectangular lattice, A or B, one of the two may be the shorter one, which we shall call the shortest lattice translation vector for this lattice. Any other lattice translation vector will be longer. For instance, suppose I consider lattice translation vector connecting the diagonal of this unit cell. This is going to be longer than A and B. Obviously, there are lattice translation vectors which are even longer, like the one shown here, or the lattice translation vector which can connect these lengths. But the shortest lattice translation vector will continue to remain A, as modulus of A is less than the modulus of B. On the figure on the right hand side, I have shown on a unit cell of this rectangular lattice all the two-fold axes overlaid. As you can see here, there are various two-fold operators, and apart from the lattice points, they are also present at the centers of the edges and also at the center of the entire unit cell. And as I have told you before, that I am, for sake of clarity, I am not drawing all the lattice, all the symmetry operators on the entire lattice, but once you obtain a unit cell, then that unit cell is translated to get the entire lattice with all the symmetry operators overlaid on the lattice. As before, apart from these rotation operators, I can also consider mirrors, and that is shown in the figure below. You can clearly see that the edges of the unit cell are also mirrors, as shown by these red lines. There are two other mirrors, the one vertical mirror and one horizontal mirror. And an important point to note as compared to the square lattice is that as there is no four-fold axis at the center, these two mirrors are not equivalent. The vertical mirror cannot become the horizontal mirror by any rotation of any symmetry axis, and therefore these are two independent mirrors, and the shorthand notation to describe this symmetry operation is 2 mm. And if I want to be a little more explicit, I will call the vertical mirror as M1 and the horizontal mirror as M2, and therefore I have a combination of a two-fold and two mirror planes, which is the shorthand notation for all the symmetry of this lattice. To make the point clear, this is the symmetry of the lattice and not merely the symmetry of the unit cell which I have chosen, but it also happens to be the symmetry of the unit cell as shown in this figure, because I have chosen a unit cell in this case which has a symmetry which is completely commensurate with the symmetry of the lattice. The third lattice which I consider is the centered rectangle lattice. It is clear, the centered rectangle lattice, as the name suggests, has a centering point apart from the four lattice points at the corner. Of course, the word centering, we have to understand clearly, is with respect to the previous unit cell. We have considered a previous unit cell for the normal rectangle lattice, and this is centered with respect to that normal rectangle lattice and not by alternate choice of unit cells, wherein the alternate choice of unit cell, as we can see, can be a primitive unit cell, in which case that unit cell will not be centered. The lattice parameters as previously for this lattice are A, B, which are independent, and alpha, which is a constraint of 90 degrees. The shortest lattice translation vector, as the previous case, happens to be A. The important thing to note here is in terms of the symmetry of this lattice, which is shown here on the right hand side for detail. Here, apart from the corners, which were originally had a two-fold axis in the case of the normal rectangle lattice, and the cell edges, which also had a two-fold axis at the center and a two-fold axis at the center of the entire unit cell, there are additional two-fold operators which are midway between the two lattice points. So, suppose I take a diagonal and I take half the diagonal, then there is a two-fold operator located exactly at the middle of the half the diagonal, or in other words, at 1/4 distance along the diagonal of the rectangle. So, there are additional symmetry operators which come into play when we are describing the centered rectangle lattice. and these additional symmetry operators are important when we actually try to decorate this lattice with a motif which will lead us to the formation of a crystal. So let us consider this centered rectangular lattice in a little more detail. What we had considered before in the previous figure has been shown here, which has overlaid on it the rotation and mirror symmetry operators, and we had stated that it has got a symmetry which is 2 mm. We could alternately choose an primitive unit cell as shown on the right hand side, which is rhombus shaped, and we had earlier pointed out that by convention we actually choose the non-primitive unit cell, which is in the colored blue, for the case of the rectangle lattices. Both the centered rectangle lattice and the normal rectangle lattice, we actually choose a rectangle unit cell, while we had a choice of making a green unit cell which is in the shape of a rhombus, which would have had a smaller size and which would have been a primitive unit cell. We shall continue our discussion of the two-dimensional lattices in the next lecture.